Hello, my name is Joshua Moore, and I'm a PhD student at Mississippi State University focused on wireless communications research. What I hope to do today is detail this research that explores partial computation offloading by breaking down deep neural networks into granular layer-level subtasks, which are then processed concurrently on IoT devices and edge servers, which hopes to reduce the transmission time and enable parallel processing within multi-mobile edge communications for IoT devices. So I'll first go over the outline of the presentation that I'll give today, which starts with the motivation for the research, the primary need of reducing DNN inference time. We'll go over the system model that's used and the foundational elements. And then I'll introduce the main contribution of the paper, which is the particle swarm optimization technique with the minimum weighting algorithm. We'll go over various benchmark and simulation results, simulating a realistic network. And then I'll give a discussion of possible R&D directions in the future and leave you with some closing remarks. So the primary motivation of this research is the rapid increase in data traffic, which is driven by advancements in wireless communications. One estimate focused on data center traffic says that we'll reach 163 zettabytes by the year 2025, which is a massive leap over now. Deep learning, known for its versatility, faces many challenges in IoT applications due to the inherent limitation of IoT devices, which limit real-time high-precision results. One promising solution was mobile edge computing, which seeks to move computation and networking to the network's edge in hopes to reduce the latency and improve task processing within wireless networks. However, mobile edge computing introduces complexities like transmission overhead and delays due to communications between the edge servers and the end-user devices, especially as the data size that's transferred between the edge servers and the end-user devices grows in size. So now I'll go over the system model, detailing the foundational elements. First, I'll describe how the fuse layer technique enhances deep neural network computation compared to traditional methods. And then I'll go over the partial computation offloading model, which is introduced in this paper. And then I'll talk about the problem formulation and the need for the main contribution, the particle swarm optimization with minimum weighting algorithm. So we can see here how linear the operation, the convolution operation for a deep neural network is, and how it's traditionally computed, which is multiplying and adding the characteristic layers in the convolution kernel one layer at a time. With this, we can see the fuse layer technique vastly improves the DNN inference time over this. What the fuse layer technique mainly does is divide the DNN into separate layers, which enables the parallel processing with multiple core GPUs. This splits input feature layers into independent segments, then merges the results for the final output, which is the same output that we would get in the traditional method, albeit much faster. This leverages processing locality for operations like convolution and pooling, resulting in a lower DNN inference time. Using the cornerstone fuse layer technique, this paper introduces the partial computation offloading method, which mainly focus on in-device and edge server communications that work together to finish the DNN inference time in lower time. With this, the edge server can process the offloaded layer from the end device as long as the edge server has processed its current task. Here we can see in the graphic that the IoT device can process some of its task and then offload that to the edge server, vastly increasing the DNN inference time. After computing all the FL paths on the edge server, their outputs are fused into a layer with values identical to a regular convolution layer. We'll further explore partial computation offloading in the next slide, which gives an example. Here we can see the FL path length is 3, and also the number of FL paths is 3. Here the path scheduling order is path 1, 2, and 3, where the FL paths are offloaded to the edge server at layer 3, 5, and 8, as shown by the red dotted line. Therefore, we can say that the computation layer's offloading strategy is 0, 0, 1, 0, 1, 0, 1, 1, 1, and the path offloading strategy is 3, 2, 2. The 2 and 2 over layer 1 means that the computation layer 1 computational time is 2, and the transmission data size is 2. We can compute the total time by considering the computation times of the edge server and the edge device, as well as the transmission time between the end device and the edge server for all layers. Next, I'll go over the problem formulation, as seen here. The objective of the problem is to minimize DNN inference time, which is a minimization problem, which focuses on the FL strategy, the optimal path scheduling, and the optimal path offloading strategy. Here we can see that DNN inference time is T, which represents the completion time of the last layer, considering computation dependencies, where we have several constraints, C1 through C4. Here, C1 models the completion time for each layer, where C2, C3, and C4 define the computation dependencies. This problem can be modeled as NP-hard complexity, where the optimization problem necessitates heuristic approaches. For DNN layers with few layers, brute force algorithm does yield optimal solutions, but as the FL path grows, brute force complexity becomes very impractical. Thus, the main contribution of the paper is introduced, which is the particle swarm optimization with minimizing weighting algorithm. First, I'll briefly introduce the minimum weighting algorithm, and then second, I will describe how particle swarm optimization with minimum weighting minimizes DNN inference times. The minimum weighting algorithm uses a heuristic approach to find the optimal path scheduling strategy and number of FL paths. Once the current path has completed its transmission, the next path should finish its computation and start to transmit without waiting is the main goal of the algorithm. The path offloading strategy, albeit, is not always the optimal solution here, so we only use the minimum weighting algorithm for the FL paths, the number of FL paths, and the optimal path scheduling strategy. Here, we use the particle swarm optimization in a coordination with this minimum weighting due to particle swarm optimization algorithm focusing on the global optimization, which is modeled after the predatory behavior of birds in the wild. They move through the problem space and try to find a global optimization instead of converging to a local optimum. The particle swarm optimization is combined with minimum weighting such that minimum weighting can set up the initial solution space with the parameters I said earlier, the number of FL paths and the path scheduling strategy, where in each iteration throughout multiple iterations, a path offloading strategy is generated. This is then compared using the DNN inference time, and if the solution is better in this instance, then we save that as the best. The constraints that guide this optimization technique are that non-negative FL path links could exist, neural network layer limits, resource constraints, parallelization considerations such as data dependencies, and application-specific requirements to ensure practical solutions. Here we'll go over an example, such as the example that we talked about for partial computation offloading. Here, above and below are different, where we can see that the optimization has taken place in the bottom one, and for the top one, we're still trying to find the optimal solution. Before updating the current path offloading strategy, OK, the best strategy in its history, OK best, and the best solution in all solution history, OK best, were shown above. We can see that the path offloading strategy is updated from its original 3-2-3 offloading path, seen by the red dotted line, to 2-3-2 in the bottom after the analysis with total DNN inference time. This before DNN inference time is 18, and we can see the improvement with the DNN inference time below being 16, a slight increase in efficiency. This would be further increased as the layers grow of the DNN, but since we have a simple DNN, we only see a slight increase here. Next, we'll talk about some simulation results, which have been extensively simulated, demonstrating the effectiveness of the proposed method. We'll talk about 5 different neural networks here, which are AlexNet, MobileNet, SqueezeNet, VGG16, and YOLO V2. This is a nice simulation since this simulates varying degrees of different neural networks, where some are light neural networks such as AlexNet and MobileNet, and then we have more like heavier neural networks such as VGG16 and YOLO V2. And we'll focus on results from 2 cases here, which show only varying the transmission rate at first, and then we'll show that when the CPU frequency of the edge server is varied. We'll show the results for that as well. So we'll first show the varying transmission rate across 5 different neural networks when the transmission rate increases from 1.1 megabyte per second to 3 megabyte per second, which simulates many different real-world scenarios. Most notably, as seen here, we can see that the DNN inference time for minimum weighting k by k and particle swarm optimization k2 with particle swarm optimization minimum weighting achieving an average reduction of 12.7 times compared to no FL, no fuse layer, right? Especially notable with a 55 times reduction in AlexNet. Furthermore, this shows the effectiveness of particle swarm optimization minimum weighting in lightweight DNNs like AlexNet, MobileNet, and YOLO V2, where it reduces DNN inference times by significant margins. Even the heavyweight DNNs like VGG16 and SqueezeNet benefit greatly from the heuristic approach with particle swarm optimization and minimum weighting, with average DNN inference time reductions of 534 milliseconds and 1251 milliseconds respectively. This demonstrates the effectiveness of the heuristic approach across a wide range of neural network architectures. Next, we'll discuss the second case, where the vary in the CPU frequency of the end device is simulated. This simulates different computing environments of end devices, where the CPU frequency is set at 1.24 to 2.11 in that range. We can see here that in both AlexNet and MobileNet, particle swarm optimization with minimum weighting 2x2 consistently produces nearly identical and stable solutions compared to optimal brute force 2x2 with minimal DNN inference times. Additionally, when considering minimum weighting k by k and particle swarm optimization k2, PSOMW outperforms all other methods, achieving the best reduction in DNN inference time, while minimum weighting k by k closely follows. Next, we'll conclude with some remarks and discuss future R&D directions. This work, as shown, introduced a novel deep neural network, parallelism, and computation offloading solution in mobile edge computing for IoT devices. This approach combined known fuse layer technique and the particle swarm optimization with minimum weighting method, which results in an average of 12.75 reduction in deep neural network inference time, shown by extensive simulations in a variety of different use cases. Possible improvements over what was shown today that I think could enhance the research would be a multiple objective optimization, where particle swarm optimization with minimum weighting is extended to handle multiple objective optimization problems instead of the just one shown here. These multiple conflicting objectives would need to be optimized simultaneously and would more realistically model networks in real life. The second possible improvement would be an adaptive offloading strategy, where more adaptive path offloading strategies can dynamically adjust based on changing network condition and device capabilities. This would more extensively handle the realistic demands of networks in homogeneous and heterogeneous use cases. And with that, I'll leave you with it. And here are my references.